The diagram shows the direction of a sound traveling in a metal sheet. It's not to scale. Particle P in the metal sheet performs simple harmonic oscillations. When the displacement of P is 3.2 micrometers and the magnitude of its acceleration is 7.9, calculate the magnitude of the acceleration when it is 2.3, right? Okay, so here's what you got to do, right? Understand that the acceleration, remember, is omega squared, the opposite of omega squared x. So notice that basically the acceleration is proportional to x. So we can just set up a simple proportion. It's not squared. If you change omega, then it gets complicated, right? But acceleration is omega stays the same. So therefore omega squared stays the same. We ignore the minus sign because they're talking about the magnitude of it, right? So really we're just looking at a and x and they're proportional, right? So you can set up a simple proportion, right? Let's see. 3.2 is to 7.9 as 2.3, dyslexics beware, is to x, right? Proportionality, there it is. All right, the wave is incident at point Q on the metal air boundary. The wave makes an angle of 54 degrees with the normal. The speed of sound is 6010. The speed of sound in air is 340. And now we're in trouble, right? Because all we've done so far in refraction is done stuff with indices of refraction. But understand that there's this formula. It's very complicated, unnecessary formula, right? So I've taught you this. N1 sine theta 1 is N2 sine theta 2. But we've got to use the one, and this is subtopic 4.4 in your data packet. So take a look at it. So N1 over N2 is sine of theta 2 over sine of theta 1, which, by the way, if you cross multiply this thing, you'll get this, which is how I feel God intended refraction to be solved. Okay, but more interestingly, this thing also does this, okay? So you can set up a proportion like that. So let's make this be 1, and let's make the air be 2, okay? So theta 1 is 54. Theta 2 is what we're trying to figure out, right? V1 is 6,010 meters per second, and V2 is 340. Okay. And now keep in mind that this is going to be a heck of a refraction angle. Okay. It's going to be very close to just coming straight out of that thing. Okay. So calculate the angle between Q and the normal and Q. So basically it's going to be find this angle, find the one that you should find. Okay. It's a small angle. It's going to be almost parallel to this, and that's because this side of the ray speeds up so much or slows down so much when it hits this, it practically stops, and it'll just come marching almost straight out of this medium here. Okay. Yeah. All right. It's a small number. In degrees, it's between 2 and 3 degrees.